And starting today, 7.4, we're going to be looking at light phenomena and optics. How can we predict how an image will form based on the properties that light shows throughout different mediums and light shows as a physical quantity? So what we're going to get started with is looking at whether light is a particle or a wave. Okay? So recall that, a particle, to differentiate between particle and wave, a particle is a tangible object that has mass. The mass can be moved from one spot to another, so kind of like electrons, neutrons, protons, so on and so forth. Whereas waves do not move, do not have mass, and they don't move from place to place. Better said, the medium that the wave passes through, which does consist of particles, does not move from place to place. The wave moves, but the medium it passes through remains in the same spot. So wave is an intangible transfer of energy from one spot to another. Energy is transferred instead of mass. And then recall that the main phenomena we've encountered so far that distinguishes a particle from a wave is that a wave can undergo constructive and destructive interference, meaning that two waves can combine to make a bigger wave, or combine to make a smaller resulting wave when they overlap. And then also reflection can occur for waves. However, we're not really going to focus on reflection here for this lab that we're going to do, or the lab that we did in class, because reflection can also technically occur for particles. Say if you throw a tennis ball off a wall, that's technically an example of reflection. So we're going to focus more on this constructive and destructive interference in order to determine if light is a particle or a wave. So for this experiment here, what we did is we took a laser beam and we passed it through a slit that split the laser beam up into two different paths. Okay, so what we did here is predicted based on if light what we would expect to see if light was a particle or light was a wave. In the case that light is a particle, we'd expect that our laser beam gets filtered out into two different paths, and we end up with these bright spots where the light hits at, or light particles hit at, and a dark spot where our light is blocked out due to the slit. All right, so this is what we'd expect to see if light were a particle. All right, now if light were a wave, that's a little bit more difficult to imagine. All right, so our main idea here is going to be to look at and see if we get the same pattern we expect for light as a particle, and if we don't get that pattern, does that show light as a particle or does it show that light is a wave? All right, so after conducting this experiment, we get a pattern that actually looks like this. Okay, so instead of getting two streams corresponding to particles, we get these bright spots interspliced, with dark spots. And so what our big question is right here is, does this support a wave theory or a particle theory? Okay. So the pattern observed does contradict the predicted pattern if light were to be a particle. So does that mean light could still be a particle and a different pattern is happening, or does it suggest that light is a wave? So the pattern here is going to be indicative of wave interference. If you recall, when we did sound waves, when I hit the two tuning forks made that wow, 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 wow sound, where they got louder at times and then quieter at times. The loudness corresponded to constructive interference, and the quietness or the low sounds corresponded to destructive interference. So we have the same thing here, except the analogy for a light wave is instead of loudness, we're going to have brightness. So the bright spots are examples of constructive interference. The waves overlap in a constructive manner and become brighter. And the dark spots are examples of destructive interference, where the waves overlap in a destructive manner and become darker. And again, like I talked about, this is analogous to sound waves from a tuning fork interfering. So as we see, light is in fact a wave, at least for now, until we get to quantum theory and some weird German dude by the name of Max Planck blows everything up. And some other weird German dude by the name of, I don't know, Einstein? I don't know, sounds like a loser's name. Definitely doesn't sound like a guy I learned physics from. Anyway, so again, here's kind of representation. Right here we have maximum intensity constructive interference, so bright spots. Then we have dark spots, bright spots, dark spots, bright spots. Blue corresponding to dark, and then red corresponding to bright. And this corresponds to what we see with our wave pattern right here in a much more simplified version. So that's what we'll be looking at today is 7.4, light wave phenomena. All right, so we'll be looking at different types of phenomena that occur for light waves. And we'll also briefly explore, although not too much, if these same phenomena occurs for sound. And that's more or less, unfortunately, over the video, that's more or less going to be my just telling you that a property occurs for sound as it does for light. So announcements, we don't need to go over announcements over here. This is a past video, okay? So our agenda for today, light wave structure and colors. We want to know what distinguishes light from other waves, what causes colors at a basic level. More to come in Unit 10. Better said Unit 9, actually. So we'll look at how colors are associated with light right now at a basic level, and then we'll explore at a deeper level when we get to quantum physics and quantum theory what specifically causes colors. Okay? So we're going to go from light waves to electromagnetic waves and ultimately up to quantum theory. All right. So we'll also look at refraction. What is refraction and what causes it? If you've ever seen a light enter a lens or a different material, the light will bend, kind of if you've ever seen the Pink Floyd album cover, Dark Side of the Moon. So we'll look at what causes light to bend through different materials. How does density and wavelength affect the bending of light? And we'll also look at polarization. What is polarization? Where have we heard about it before in everyday life? And what specifically is going on in polarization? So light waves. So light is a wave that transfers energy from one location to another. This energy is what we feel as thermal radiation, the third form of heat conduction. Back in Unit 6, we covered two forms of heat conduction, or excuse me, not heat conduction, but heat transfer. We covered two forms, conduction and convection, but we did not cover a third form, mainly because the third form we had not gotten to a point where we could state what that third form was. But now we can state that third form of heat transfer being thermal radiation, energy carried by light waves. So the energy of a light wave is proportional to the amplitude of the wave, all right? Just as with any other wave, the amplitude of the wave dictates how much energy our wave has. And then the wavelength of light governs the colors that we see. So blue corresponds to shorter wavelengths / higher frequencies, and then red corresponds to longer wavelengths / shorter frequencies, okay? Actually, do I have this mixed up? No, I got this correct. All right, good. All right. Now, the big thing that distinguishes light waves from other waves is that light does not require a medium to move. Light can propagate throughout the vacuum of space without ever having to have particles colliding to transfer energy. So there's no particles required in a medium for light to propagate and light to move. Okay. Now back to the wavelength of light. Okay. So hold on to this right now. Again, we're only covering this at a face value, but we're going to come back to colors and light waves when we get to quantum physics. Specifically, hold on to this idea of red and corresponding longer wavelengths, because it actually turns out this is how we know that the universe is expanding and getting larger. It has to do with the wavelength of light and the colors we see from distant astronomical objects. So light also consists of wavelengths we cannot see. So light is part of a larger spectrum called the electromagnetic spectrum, and there are other versions of light waves. And I say light in quotations because they're not really light waves, but different forms of a larger set of waves, again what we call electromagnetic waves. So there are also radio waves, microwaves, infrared, and ultraviolet. We do not have to worry about these right now. Again, we're covering light at a fundamental level. We'll come back to what all these different regions and all these different types of waves correspond to when we get to electricity and magnetism. Right now, unfortunately, it's not the appropriate time to cover these types of waves because these types of waves are better covered when we get to electricity and magnetism. And just for reference, again, you don't need to know any of this stuff, but here's the light wave spectrum. Longer wavelengths, all right, again, corresponding to red. Shorter wavelengths corresponding to blue. We can see that the wavelengths also correspond to temperatures as well. We'll take a look at this when we get to quantum theory. Actually, I'm not sure we will get to this when we cover quantum theory, because this goes more into the ultraviolet catastrophe in Wien's law. So we may or may not cover this, all right? But again, still, this does convey the idea that our light waves do carry energy in the form of thermal radiation, okay? And then we'll come back to electromagnetic spectrum back in when we get to Unit 8. So for right now, a really cool thing to show you here is, again, this idea that there are colors outside of the spectrum, visible light spectrum, that we cannot see. And I can't tell you the most specific reason for it. I'm not a biologist or I'm not a biophysicist. But the basic idea, if I recall correctly, is that the cones and rod cells that make up our eyes, allow us to see, do not have the proper, I would say, adaptations in order to allow us to see colors outside the visible light spectrum. So here's a really cool video of what the sun would look like if we were able to see the different colors of the different wavelengths of light that are emitted by the sun. And of course, it's put into colors that we can understand, so that's more visually understandable for us. Okay. So here's all different colors that we can see right here, or would be able to see, corresponding to all different wavelengths of light emitted by sun that we cannot see because our eyes are not attuned to see these colors or to see these wavelengths. Alright, so a pretty cool video, or at least I like to think so. So now let's move on, okay? So we have this light waves investigation activity that we do, okay? You're free to explore it at your own accord, but this is just a video lesson, so we're going to skip over this, alright? So basically we're going to be, or in this lab, we're investigating what's called refraction, which is the bending of light as it enters a new material, okay? So there are two factors that affect refraction: density and wavelength. And the goal of this lab here, if you wish to explore, and I would encourage you to do so, is to determine how refraction occurs based on these factors. How do these factors cause refraction to occur, and what is the relationship between how much light is bent and the density of our material? All right. So here's the idea behind refraction, reflection. I always mix up these two words. Blech. Good thing I'm not an English major. Good thing I didn't major in English in college. Or perhaps linguistics, better said. So when light passes through a new medium, part of the light will be reflected, while part of the light will pass through. Just like if you look outside of a car window, somebody on the other side will be able to see your image because the light that you emit passes through the window. But at the same time, you will also be seeing reflection because some of that light is reflected back towards you. Okay. So reflection, the light is reflected at the same angle as it hits the medium. All right. So the angle that our light hits a medium, say like a mirror, is going to be also the same angle that our light is reflected at. Hence, we call that reflection. Reflection is it has a symmetry to it, a symmetric property to it. Okay? And then refraction, some of the light passes through and changes direction. So when our light passes into a new medium, the light is going to change direction. So the amount by which the light is refracted is dictated by two factors. The density of the new medium, the higher the density compared to the old medium, the more light is refracted. And then the wavelength of light, the shorter the wavelength, the more the light will be refracted, okay? So this is what was explored in the lab. And then on the next slide, our goal here is to combine these two factors to explain why light is refracted, okay? So again, density has a direct relationship with refraction. The higher the density compared to the old medium, the more light is refracted. And then also wavelength has a inverse relationship with refraction. The shorter the wavelength, the more light will be refracted, all right? So here's an example of refraction you may have seen in your everyday life, okay? When a straw is put into, say, a liquid like water, okay, the straw's light is going to be bending as it passes through the new material. It's going to be bent at a new angle, which is going to cause a straw to appear like it's moved at a different angle than what it originally entered at. So this is an example of refraction right here. So refraction and reflection part 2. So here's the theory of refraction, why it occurs, at least without going into the nuts and bolts of quantum optics and all that crazy stuff, okay? So the density, the waves slow down as the medium becomes more dense. Recall the gummy bear lab, and this is described by the index of refraction. Now the index of refraction does not always have to correlate with the density. I would imagine if I were a material scientist, there would be 1 or 2 materials that don't display the relationship I'm stating here. But more often than not, the higher the density of material, the higher the index of refraction. Okay? So if the density increases, the waves are going to slow down. And so what this causes to happen is that for a constant frequency, say we have a light of a single source of a single frequency, a decrease in wave speed will decrease wavelength. So a decrease in wave speed right here is going to cause a decrease in wavelength if we have frequency constant for a single source of light, say like a white light right here, okay? So as a result of that wave speed decreasing due to an increase in density, the wavelength is also going to decrease, and what's going to happen is that our light is going to bend towards these shorter wavelengths. So for example, if we have white light right here, white light actually consists of all different colors. As the light enters a new medium, the white light slows down, and that corresponds to a decrease in wavelength, okay? And so that's going to correspond to different wavelengths decreasing, and that's going to correspond to different colors appearing, okay? So for example, red is going to tend to have a longer wavelength, whereas purple is going to tend to have a shorter wavelength, okay? So we're going to have the shorter wavelength right here, this longer wavelength at the top, and what's going to happen is that the light is going to bend towards the shorter wavelength. Just like if you bend a slinky down, you'll notice that the part where the slinky is bent down towards is most compressed. And that results in the bending of light. And so as distance goes on, this bending becomes more and more pronounced as our objects become more, as our colors become more and more separated, and that allows us to see the different colors that make up white light. Purple light right here, and then red light at the top. Kind of just like the famous Pink Floyd album cover. All right, and so a brief aside right here, we can also look at total internal reflection. So if a light passes from a more dense medium to a less dense medium at a certain angle, the light will be entirely reflected, and this is known as total internal reflection. Okay? So we're not going to go into the mathematics of total internal reflection because it is it involves a little bit of trigonometry. If any of you are interested, it's kind of based on a law known as Snell's law, and then it applies a little bit of trigonometry to Snell's law to figure out the minimum angle that's required, okay? But essentially when this angle is met, this critical angle is met, all your light will be internally reflected, okay? And as a result, what you're going to have is you're going to have an image that seems to bounce, an image that appears right here as all the light is reflected off of, say, our fish back towards us, all right? So if you've ever been in an aquarium and you've ever looked up at the top of the aquarium water, you'll notice that if you look at just the right angle, the light will be reflected out towards you. You can see the reflection of fish, and that is an example of total internal reflection. All right, so here's a think, pair, share for us here. At right are diagrams for 4 hypothetical light waves. We want to rank the energy of each light wave from least to greatest. And then we want to rank the amount of refraction each wave would undergo if changing media. All right, so we have number 1 right here. Number 2 is this wave right here that I'm tracing out right now. Let me trace that again because I didn't do the best at it. And then number 3 is this wave right here. So take a moment to answer, and then we'll bring it back together and go over this together as a class. So looking at the energy of our light wave, okay, going from least to greatest, remember that energy is proportional amplitude, so we need to be looking at the amplitude of each light wave. In this case then, all right, 3 would have the least amount of energy, or excuse me, why do I have 3 as least here? No, that shouldn't be 3. So 2 should be the least. 2 should have the least amount of energy because it has the least amplitude. 3 should have the second most amount of energy since it has the second highest amplitude. And then finally, wave number 1 should have the highest amount of energy since it has the highest amplitude of the 3 waves. So my ranking is a little bit off here. I'm not sure what happened here. Maybe perhaps a typo. And lastly, for refraction, okay? So the wavelength is going to dictate how much refraction occurs here. Again, so we need to think about the factors that affect refraction and how can we determine those factors from our graph here. So again, refraction is determined by the wavelength of your light. So if we're going to be looking at which one undergoes the least amount of refraction, we need to look at which one has the longest wavelength here. All right? Or better said, shortest amount of wavelength. Actually, no, I have my rankings off here again. Dang. So I'll have to fix this. All right, so remember, because the inverse relationship with refraction and wavelength, okay, that we need to go ahead and look at the shorter wavelengths, and those shorter wavelengths are going to be the one that are most refracted. So in this case, 3 has the shortest wavelength. No, I actually do have this correct. 3 is the shortest wavelength here. I'm all over the place right now. 3 has the shortest wavelength, thus undergoes the most refraction. All right, 2 has the second longest wavelength, so it undergoes the medium amount of refraction. And then lastly, number 1 has the longest wavelength, so number 1 would undergo the shortest amount of refraction if put in, if all these waves were to enter a new medium. Okay, so 3, 2, 1, 3 with the most refraction, 2 with the second most, and then 1 with the least amount. And then for energy, energy should go, for our rankings, it should go 2, 3, and then 1. 2 having the least amount of energy, 3 having the second most, and then number 1 having the most energy. And then lastly, we come to our last topic, which is polarization. So polarization. So light waves are generally oriented in random directions without any sort of preference. So when you emit light from a light beam, all right, the light is generally going to be unoriented, meaning that you're going to have light waves in all different directions. For simplicity's sake here, we're going to look at the horizontal and vertical directions, okay? So a light wave that's oriented in a certain direction is said to be polarized. How do we polarize light? So what we have are what are called polarization filters that can be used to filter out light waves of a certain orientation. So a filter oriented in a certain direction only allows light oriented in that direction through, all right? So for example, this polarizer is vertically oriented, so only vertically oriented light will pass through, and as a result, horizontally oriented light is blocked out, and that reduces the intensity of light. So if you've ever seen polarized sunglasses are used to reduce the brightness of light, and the idea being is that the sunglasses only filter through certain oriented wave orientations of light, thus reducing the brightness that impinges on your eyes. Perhaps better said in physics terminology, the light intensity that impinges on your eyes, the luminosity. All right. So as polarizer, you can kind of think about like a fence filtering out the light, except it's not like you can take toothpicks or really thin objects and stack them up and create a polarizer. That's not how these polarizers work. These polarizers actually work on the principles of electricity and magnetism, which unfortunately we have not gotten to yet. So we are going to save for how polarizers actually work when we get to electricity and magnetism. And actually, when we get to electricity and magnetism, you'll be surprised to find out that polarizers, say a vertically oriented polarizer like this, actually has lines that run horizontal. And we'll learn about the reason for that when we get to our unit on electricity and magnetism. So lastly, we come to a think, pair, share. So unpolarized light is passed through a vertical polarizer and then a horizontal polarizer. We want to know, before hitting a screen, we want to know which way will the light be oriented after it passes through a vertical polarizer. Will it still be random orientation? Will it be vertically oriented, horizontally oriented, or no light at all? And then what will the light look like after passing through the horizontal polarizer? So let's go ahead and take a look here at our result. So here is some randomly oriented light. If we pass it through a vertical polarizer, we see the light becomes vertically oriented, as we would expect. All right. So now let's see what happens if we pass this vertically oriented light through a horizontal polarizer. Well, as we can see, the horizontal polarizer is only going to allow through light oriented in the horizontal direction. So as a result, this light is going to be completely blocked out. There's not going to be any light getting through. And in fact, if you have two really good polarizers, you can actually do this, turn one sideways, overlap the two, and the light will actually be completely blocked out. And you can actually use that as a quick kind of little layperson's test to determine how effective a polarizer is. Is it a good polarizer or a bad polarizer of light? So we are not done with light waves. In fact, everything from here on out in this class is influenced by the physics of light. So more of the theory of light will be explored in electricity and magnetism, Einstein's theory of general relativity, and quantum mechanics. Electricity and magnetism with Emperor Palpatine, general relativity when we get to black holes and how gravity works, and then quantum mechanics. How does light have to do with quantum mechanics? What is quantum mechanics besides something that just gets name dropped in science fiction movies all the time? Well, we'll find out down the line in this class.